welcome back. In this video, we'll talk about interpreting one-dimensional motion in a graphical sense. So, let's say you have an acceleration versus time graph, and your acceleration is constant. So, along this graph, the acceleration will remain in a straight line for however much time because it's constant, it's the same. So, the area underneath it, let's say this is t sub I and a sub I, the area underneath this graph is going to be the change in velocity. Why is that? In the simplest sense, think about the units of acceleration. Let's say it's in meters per second squared. And for time, let's say the units are in seconds. When you find the area of this rectangle, you're going to do base times height. So your units will be meters per second squared times seconds. The seconds will cancel and you're left with meters a second. So that's why the area underneath this graph is your change in velocity. So if that's the case, then you could substitute change in velocity for the area of the rectangle. For base, you could substitute t for ti, we'll just say t here, and for h, you have a. Alright, now let's look at the graph for velocity. Now, acceleration is a rate of change of velocity. In other words, if you integrate acceleration, and acceleration is constant here, let's say it's a, and you integrate it with time, you're going to get at plus some constant, and that constant being your initial velocity. If you were to write this out here as your final velocity minus your initial velocity equals acceleration times time. So your final velocity is equal to your initial velocity plus acceleration times time. So the c is the initial velocity. And this should show you that if velocity or acceleration is constant, then the velocity is linear. So let's say this is vi, your initial velocity. It's going to be linear and it's going to have a slope of a. So this graph has a slope of a, the acceleration. Now why is that? Say your initial velocity was 5 meters a second. And let's say acceleration is 2 meters a second squared, or 2 meters a second per second. So after the first second, he's going to add 2 meters per second onto it. So it's now going to be going 7 meters a second. Then after another second, he's going 9 meters a second. Then he's going 11 meters a second. And this change is a constant change, which really should tell you that the graph is linear. So if you don't know what integrals are, that's another way to view the graph in a way to see that the velocity is linear. Okay, so the velocity is linear and has a slope of this acceleration. Let's say we have some final velocity up here. Note that the difference between these is the change in velocity. Well, the area underneath this curve, in this case, is going to be your displacement. Now, the area underneath this curve is displacement because if you take an area, you're going to be multiplying, meters is per second unit times a second unit, and you're going to be left with the meter unit. So that's in essence why this is the way it is. Alright, so if you look inside here, you're going to want to split this up into two areas. So you draw a dividing line here. This just makes it easy to calculate the area. Well, the area of this one here is the area of this rectangle, and here's the area of a triangle. So the total area, or the displacement, is equal to the area of the rectangle plus the area of the triangle. The area of the rectangle is VIT. The area of the triangle is 1/2 change in V times T, and change in V is equal to AT. So you get the displacement is equal to the initial velocity times time plus 1/2, and you put in the AT rather than change in V, 1/2 AT squared. So that the area of these two shapes down here together is the total displacement. Alright, when you look at these three graphs, this is basically what you have. If your acceleration is constant, then your velocity is going to be linear, and your position is going to be quadratic. So here's the position with time. This one, velocity, is really just the change in position with the change in time, and acceleration is really just the change in velocity with the change in time. And change in velocity with change in time is just change in position with change in time. So the velocity is the derivative, if you want to think about it this way, the velocity is the derivative of the position, and the derivative of the velocity is acceleration. Now going backwards, if you integrate the acceleration for some time interval, you'll get the change in velocity for that time interval. So what you're getting is the area underneath that curve when you integrate. So that is the change in velocity. Now, when you do that with the velocity graph, which when you integrate you get a linear function from a constant, when you do this with the velocity graph, using basic dimensional analysis too, you can verify, meters a second times second, well that's meters. This will be your displacement. And integrating from here in this, that gives you your area underneath that curve for that time interval. And if you integrate in general without putting in, t equals 2 seconds or something, but just have t, you actually get a quadratic function. Now from here, the area under this quadratic doesn't really mean much, because if you notice, if you take that area, you're just getting time per meters, and time meters, and that doesn't really make much sense. But if you take the tangent line at any point on this graph, you actually get the instantaneous velocity at that point in time. So let's go ahead and take an example and see what kind of problems we can work with this graphical understanding. Alright, so let's say you have a plane and it lands at 250 kilometers an hour. Alright, and after 30 seconds it comes to a halt, and it is now going, obviously if it's at a halt, it's going 0 kilometers an hour. We're interested in the shortest runway possible for that to occur in 30 seconds. Alright, for this problem, we're going to have to assume that acceleration is constant. And since acceleration is constant, since we're assuming that it's constant, the velocity will be linear. So we're going to go straight to drawing a graph. It's velocity versus time. Alright, so our initial velocity is 250 kilometers an hour, and that's at 0 seconds. So we'll go right here. And this is 0, 250. Alright. And then real quick, let's convert seconds to hours, which will be 30 seconds times 1 hour over 3600 seconds, which is 30. That seconds will cancel. You get 30 over 3600. And you get 3 over 360. And you get 1 over 120. Alright, so this is 1 over 120 hours. So we'll put that right here. So this is 1 over 120. So after 30 seconds, the velocity is 0. Alright, now if the displacement is the area under the graph, and acceleration we're assuming is constant, so the velocity is linear, so the area underneath this is the displacement. Alright, so the area of the triangle, or the displacement, is equal to 1/2 the base, which is 1 over 120 hours, times the height, which is 250 kilometers per hour. Hours cancel. Right. See, the hours will cancel here. And you are left with, let's see, this becomes 250 times 120 divided by 2. This becomes, 250 divided by 120 divided by 2 becomes, the displacement is equal to 1.04 kilometers. We could convert that to meters by multiplying by 1,000, and we get 1,040 meters. So the runway needs to be 1,040 meters. All we did is we plot the initial point and the final point. Since the acceleration is constant, velocity is linear. Find the area underneath the curve. That's the amount of distance that plane's gonna. Thanks for watching.